All right, so it doesn't make any sense for me to just put the answers on a key when it comes to the Boolean simplification problems. That's not going to do you any good. You actually need to see the path that one might take to get there. So what I'm going to do is work the problems on the practice sheet so you can see at least the path I took or I take to get there. Now, mind you, the way I take to get there may not be the way you take. There are any number of different routes one can take to get to the final reduced expression. Uh, Unlike math, which often follows a very strict do this, then do this, then do this, then do this. Logic isn't like that. Logic, as long as you're applying the laws properly, it doesn't matter. You can take 2 steps or 100 steps. It just doesn't matter. So there are a number of different ways you can take to get to a place. Now, as with most computer scientists and engineers and stuff, there's always this like, I did it in 2 steps, versus, and that's important. Efficiency is really important, which I always like that about engineers and computer scientists, that they really strive for that. That said, it reminds me of this joke. What do they call the person who graduates last in medical school? Well, doctor, of course. Now, mind you, such a person probably has more lawsuits than patients, but, little details of life, whatever. Point being, as long as you get there and you apply the laws properly, it doesn't really matter how many steps it takes you to get there. Don't worry about it. Many times I've gotten like halfway, 3 or 4 steps down and gone, oh my goodness, I really could have just made this so much shorter if I'd just done this, 3 steps ago. So, with that in mind, this video is going to be fairly long. Don't fret. It's actually a series of videos crammed into one giant video. I'll try to produce a table of contents for it so you can see where each problem happens. The first part of the video is we're going to go over the rules again. And then after that, I'm going to go over each of the problems in the practice set. So it will be fairly long, and I may do some of those a couple of different ways. Don't worry about it. It's fine. Okay. With that in mind, let's look at our rules again. Oops, don't do that. Come back here. Okay. Now, as we said before, this is just what I think is the standard set of rules one tends to find. There's no, I shouldn't even use the word standard. This is the common set of rules one tends to find. That's a bit redundant. There is no standardization for these rules. Some systems include absorption, some do not. You don't really need it. You can actually usually get to absorption via a series of distributions. So, whether or not it's there, don't sweat it. In fact, you'll see if you do logic long enough, if you keep doing problems, you'll start seeing things over and over and over again, and you'll start thinking, that should probably be a rule, which, publish a book or a course or something like that and include that as one of your rules. That's just the way it happens. Okay, just not for the exam. It has to be a set of rules we agree upon. So, yeah, okay. All right, our first rule, of course, is the double composition, not composition, the double complement rule. And that one's really easy to see. And it just says not A is the same thing as A. And that's really very straightforward. If A is, if A is 1, then not A is 0, and not A brings us back to 1 again. So pretty straightforward. This is the only rule that doesn't have both a conjunct part and a disjunct part. You'll note that all the other rules do. They come in, I put the conjunct part on this side here and the disjunct part over here. So we'll go through those. All right. The next one, the complement rule, basically states, for the conjunct, states that A and not A is equal to 0. And that's easy enough to see, because if A is 1 and we have not A, that's going to be 0. True and false, of course, is going to equal false. If A were 0 to begin with, then false and anything is, of course, going to be false. Okay. The disjunct portion of it says A or not A is equal to 1. And that makes sense too, because if A is 1, well, 1 or anything is going, true or anything is true. And if A is 0, then not A will be 1, and false or true is still going to be equal to true. Let's see. Note that A and not A is a self-contradiction, by which I mean, as we saw previously, that it's false in all possible truth circumstances. So you can see this in it. It's like saying, well, it's both alive and it's not alive. A exists and it doesn't exist. That's crap. It can't be the case, so it always results in a 0 or a false. The or statement of this rule, A or not A, is a tautology because it's true in all possible true circumstances. Well, it either is or it isn't. Yeah, well, thank you for stepping up and, taking a stand on that. I'm either for the movies or not for the movies. I don't know. It's just true in all possible circumstances. I'm either coming to your party or I'm not coming to your party. Well, I knew that much, right? So it's a tautology because it's true in all possible circumstances. Abbreviate that as tout. And this is a contradiction. There really is no nice abbreviation for contradiction. Otherwise, it might be contrary. Anyway, contradict. T-I-O-N. Okay, contradiction. So, all right. Now, this has a relationship. It's a very interesting property that coincides with this. At any given point in an expression, so you have some expression going along here, you can add an and one to it, an and true. The reason being is this. If this were false, well, then adding an and one to it doesn't change anything because false and true is still false. If it were true, then you're just adding a true to a true, so you're not really changing the expression, the value, the truth value of the expression. So at any given time, you may add an and one or any equivalent of an and one, and you'll note that we do have equivalents to one. A plus 1 is equal to 1. So you could add and A plus 1 because that's equivalent to 1. So you can add that at any time. Same thing with the, same opposite thing with the disjunct. At any given time, at any given point in an expression, you can add an or 0. And the reason being is if this were true, adding a false to it makes no difference. True or false is still going to be true. It maintains its value. If what you're adding it to were false, then you're just adding a false to it. You're just oring a false to a false. So false or false is still going to be false. You're not changing anything. You'll note that there is a 0 up here under the dominance. So we have, we could add then the equivalent of 0, which is we can add or A and 0. That can be useful when duplicating certain things or the like. Also, we can add complements in the same way. We could add or A and not A simply because that results in a 0. So we're not changing whatever came before it. Over here, we could add and A or not A because adding a 1 here won't change adding a 1 via the conjunct and won't change the value of the unit you're adding it to. Okay. Hopefully that makes a bit of sense. It's actually very useful, especially these lower ones. What you end up doing is mirroring something that came before, and then utilizing that to create doublets that you can then cancel out, etc. None of these problems are like that, though they could be worked that way. So, all right, moving on then. The identity, the dominance, which we kind of went into. Any statement of A and 0, of course, is going to result in 0 because you're simply adding a false already in there, right? Or not adding a false, I'm sorry. There's a false present in a conjunct, so you know that whatever A is doesn't really matter. The end result is going to be 0. The same but opposite for the disjunct. A or 1 is always going to equal 1 because there's a truth there already in it, and you only need one true statement, one true element to make the expression true. So the A, again, doesn't matter. Okay, so that's our dominance rule. Pretty straightforward. Okay. Idempotent, it's a tough word to pronounce, idempotent, which is here, says it's our collapsible. It's our rule of collapsing, or our doubling rule, or however you want. It depends on which way you're going. And you can work these rules either direction. You can work them. We'll look at that. So if we have any statement of A and A is going to equal A. And that's easily seen because if A is 1, then you have a 1 and a 1, which is going to equal 1, or true and true, which is going to equal true. If A is false, then you have a false and a false, which is, of course, going to equal false. So whatever A is here, it's just going to collapse onto itself as itself. Same with the or statement, or the disjunct. A or A is going to equal A, because if A is a 1, well, then that's enough to make the overall statement true. If A is a 0, then it's a 0 in both spots, or false in both spots. False or false is going to equal false. So no matter what A is, if you have A or A, you're going to end up with A. Now, like I said, we see this most of the time in this form here, where you have, oops, hold on a second, this eraser is always very small and somewhat annoying to deal with. You can make it bigger, but it's really kind of, there's no real simple, quick step to do that. Okay, so we usually see it like this, where you have A, and that's just going to allow you to produce A. But if you did have a singular A, you can simply duplicate that as A and A. That's not terribly useful, but from time to time, you know, there might be a moment where you might find some benefit in doing that. Just so you know that you can work the rules from this form that way, or from this form that way. It doesn't matter because they're equivalent. They're interchangeable. Okay. The association rule is really very easy to see. People don't generally have a problem with that. Any statement of A and B and C can be reassociated together as A and B and C. And it doesn't matter. It doesn't have to be just 3. You can do 4, 5, whatever. Again, unlike propositional logic, which is limited to binary statements, Boolean logic is not. So in this regard, you can actually just get rid of one of the parentheses, and it works because of this. You could reassociate like that. It works because of this. If there's any zero in any of these, let's say you have one, and let me go back here for a second and put it back like that. Let's say you have 1, 0, 1. Well, this 0 here is going to make this 0, which will make the overall statement 0. If you had 0, 1, 1, well, you'd have a 1, you'd have a true here, but the 0, the A being 0 makes the overall major operator 0. So you can see it doesn't matter what, if you have a 0 anywhere in there, it doesn't matter how you group them together, it's still going to come up false. So these can be reassigned however you like. Same with the OR statement. A or B or C can be reassigned as, reassociated as A or B or C. And again, if there's a 1 anywhere in here, it's going to be true. If B is a 1, then true or anything is true. Anything or true is true, so that's fine. If A were a 1, well, true or anything is true. If C were a 1, this is going to make this true, which will make that true. So as long as there's a 1 anywhere in it, you're going to get true. So you can reassign these, reassociate these any way you'd like. Okay. Commutation, pretty much the same thing. 1 and 0 is the same as 0 and 1. A and B is going to be the same as B and A. Same for the disjunct side of it. True or true, or true or false is still just as true as false or true is. So true or false is still going to be true. False or true is still going to be true. So A or B is the same as B or A. It doesn't matter. Okay. Distribution is a little more interesting and somewhat, sometimes a little bit difficult to see. If we have A and B or C, we can distribute this conjunct over the disjunct is the way it's usually put. And that then becomes A and B. So we're like, note that we are swapping our major sign becomes our minor sign. So it's A and B or A and C. So A and B or A and C. Okay. If A, if A is 0, then the overall statement here is 0. If A is, then here, if A is 0, that makes this overall statement 0. And here A is 0, making this overall statement 0. So we have equivalence if A is 0. If A were 1 and B were 1 and C were 0, then we would have a true here. This becomes, sorry, let me finish this. True or anything becomes true. True and true is, of course, true. It's our overall statement. So here A is 1, here A is 1. B is 1, making this true. True or anything is true. So they're the same here. If B were 0, and C were 1, we would get pretty much the same situation that we just went through, except that you'd get 1, 0, but you'd get 1, 1, making this true here. 1 or anything is true, true and true is true, so they're the same. If both these were 0, then this becomes false. True and false, of course, is false. But if both B and C are 0, then these individual terms here become 0. And so 0 or 0 is 0. So you can see that no matter what the situation, these always produce, these two propositions, these two expressions always produce the same truth value. They are equivalent. They can be interchanged at any time. The same, of course, holds true for its opposite, any statement of A or B and C. We can distribute the disjunct over the conjunct in this case, or maybe it's better to say we can distribute the major operator over the minor operator, thus switching their places. So A or B and C becomes A or B, A or B. And note that our major operator has now become our minor operator, and A or C. Okay, so A or C, like that. All right, let's see. One of the things that makes this challenging for people is the fact that sometimes it's very hard to see these things. So if you have some statement like, especially if you're going this way, if you have some statement like M and X or B and M and X or C, you can pull these two out because these basically take the form, this is A or B, so A or B, and this is A or C, A or C. So this really is a form or an instance of this form. So we can then go ahead and just distribute this by pulling the M and X out as M and X. Our minor sign becomes our major sign, and then our last two get linked together via the major sign. So the minor sign becomes the major sign then becomes the minor sign, linking together the last two terms, B or C. That's not right. Try that again. B and C. I just got through explaining that too. Okay. Anyway, so that's, it can be worked, you can see that it can be worked in both directions, and it doesn't have to be a straight A or B or a singular term. You can have a full unit as long as it's a unit we're looking at. This unit, if it has exactly the same unit, and the parentheses are making this a unit, in this case over here, I should say they don't necessarily have to be there based on precedent, which we'll get to in a minute. But as long as you have the same unit here and the same unit here, they can be pulled out as a pair. Okay. All right. So moving forward, absorption is really, really quite odd. And it tends to seem almost mystical at first. It's like, well, what happened to the y? Why does the y just disappear? And we'll show you what happens here. Any sentence, any proposition, any expression in the form of a and a or y is going to equal a. And here's the reason. If a is a 1, then a is a 1 here. That makes this true, making true and true. Oh, my goodness, I just really did that, didn't I? Sorry, that should be an a. Any statement, a and a or y is going to equal a. A simply dictates because it commands over both the disjunct and the conjunct. So if a is a 1 here, it's a 1 here. 1 or anything is 1. 1 and 1 is 1. So if a is a 1, then we're going to get a 1 out here. If a is a 0, well, 0 and it doesn't matter is going to equal 0. So if a is a 0 here, we're going to get a 0 here, which is a. Okay. The same holds true for the disjunct side of it. Get rid of this for a second. There we go. A or a and y is going to be equal to a. Because if a is a 1 here, then 1 or anything, wow, that was nice. Okay, 1 or anything is going to equal 1. If a is a 0 here, then it is also a 0 here. A 0 and anything is going to equal 0. 0 or 0 is going to equal 0. So if a were a 0, then it will be a 0 here. So no matter whatever a is what we get on the outside. And again, it's because a is commanding over both a conjunct and a disjunct. Note that the signs have to be, for this rule as stated, the signs have to be different. A or y is not the same rule. It may be quite clear to you that if a is a 1, you're going to get a 1 out of here. However, if a is a 0 and y is a 1, we're still going to get a 1 out of here, so it doesn't apply, right? So be careful of that. Make sure that we have opposite signs, okay? That's very important. All right. Let's get that. That brings us finally to De Morgan's. And this basically states that for any statement of A and B complement or negated is going to be equal to A complement, change the sign, or B complement. Now we can see that fairly readily on a truth table. If A is 1 and B is 1, then our statement is 1 negated becomes false. Here, A negated becomes false, and that will be enough to produce a false. So they're the same if both of them are 1. Wow, that was really bad. If A were 1 and B were 0, that would make this false negated becomes a true. Here, A is 1, negated becomes a false, but B is false, negated becomes a true. False or true, of course, is true, so they're the same here. It works exactly the opposite, or exactly the same for the opposite way, however you want to look at that, with the A statement, because if A is 0 and B is 1, then we do the same thing. This false and true is false, negated becomes a true. Here A is false, but it's negated, so it becomes a true. True or anything is true, so they're the same again in here. If both of them are false, then this is false, negated becomes a true. Here, if both of them are false, they are both negated to a true. and true or true, of course, is true. So again, it's the same. This works in the opposite as well. You can move from, because they're equivalent, if you have a statement of A complement or B complement, you can simply write that as A and B, that whole statement negated. We do have a disjunct side of it. It seems a little bit almost, well, we do have it. So it's A or B, that whole thing negated is equal to A complement and B complement. And again, if these are both 1, that's 1 negated to a 0. Here, this is negated to a 0, 0, and anything is 0, so they're the same. If A is 1, it's still enough to make this whole statement 1. Negated becomes a 0. If A is 1, it becomes negated to a 0, which is enough to make this whole statement 0. So they're the same here. If A is 0 and B is 1, false or true is still enough to be true. Negated becomes a false. Here, A is 0. Negated becomes a 1. Here, B is 1. Negated becomes a false. True and false is still false. So they're the same here. If both these are 0, then false or false is false. Negated becomes true. Here, false negated becomes a true. False negated becomes a true. True and true is, of course, true. So these statements are equivalent, and they can be replaced, exchanged for one another at any given point, as are all of these laws are equivalency laws and can be exchanged for each other across the line from one form to the next form within the law at any given time. Okay. Next thing we want to look at then is precedent. And Boolean logic does have a precedent. It's not as predominant as, say, your PIMDOS or anything like that, simply because I don't know, it's more obvious, I think, and so people just don't really pay attention to it. It's just more of a, well, of course you have to do that, with one possible exception, and that's the conjunct rule. But we're not going to start there. The primary precedent for Boolean algebra is the negation. So we always do our negations first, and if you're given, say, something like this, you need to figure out what not A is first. You need to figure out what this is first. And here's why. If you were to do this and then negate it, we might end up with a different situation. So if we, say, had a 1 and a 1 here, 1 gets negated to a false. We still have a 1. That's fine. So this equals 1. But if we did the negation, if we did the disjunct first and then negated it, we're actually doing something where we're doing this first and then we're negating that whole thing. So here we have 1, or 1 is a 1. That negated, however, becomes a false. So in this situation, you can get a different answer if you were to work the disjunct before you worked the negation. So we want to be very careful that we're working our negations in the proper order. If it swings over the whole operator like this, then you do the operator first, then the negation. More often than not, you would end up using the De Morgans to part it out into A and A complement and B complement and deal with it that way, or you deal with it as a whole negated unit. such as the form, you'd be dealing with it as the form of this is simply, this whole thing is some p and it is negated, so you could move it around as a single unit like that. All right. Nonetheless, deal with your negations first. Utilize the De Morgan's rule or keep them as a single unit. And you have to. You can't put anything into this. You can't distribute anything into this or pull anything out of it until you're dealing with, until you've dealt with the negation. And what I mean by that is if you had x and a or b overall complement, you cannot distribute this into this because it's bound up by the negation. You have to deal with that negation first, so you have to actually take this and say x and not a and not b. Now we can reassociate. We can't distribute because our signs are not different. In order to distribute, we have to have different signs. Here our signs are the same, but we can reassociate as necessary or something like that. Want to look at this real quick. Get rid of this. What we have here is a NOR gate, really. Where's my, hold on, I've lost my pen. Come on, that's stupid. 1 second. What we have here is a NOR gate. So this is the circuit for this, the gate for this is an OR gate with A coming in and B coming in, and A is negated. And we get some output here. Here what we have is A and B come in, and the overall output is then negated, and we denote that by putting a little ball in front of the gate and doing that, which this is exactly the same as saying of doing something like this. Okay, so this is called our NOR gate. There's also a NAND gate. So any statements, let me get rid of this real quick. If any statement of A and B, that whole statement negated, looks like it's an AND gate. So we have an A coming in and a B coming in. And then the output of that is negated. So we put a little dot in front of it, a little ball, and that is called a NAND gate. It's interesting because the word is somewhat backwards. It looks like not and, but really it's and not. Whatever. Just be aware of that you have to deal with the negations before you deal with the other things. Okay. Okay, so the next precedent is the disjunct over conjunct. Excuse me. Disjunct does take precedent over conjunct. So what I mean by that is, given the statement A or B and C, that really needs to be viewed as A or B and C in parentheses. That is, this takes precedent over this. We have to do this part first before we can do the disjunct. So we do the conjunct first, and then we can deal with the disjunct. This means that the parentheses here are not necessary. They're redundant in a way. I like to put them in because it keeps my brain straight, and that, as we all know, is not always an easy task. And it is really common to try to work this problem left to right. simply because that's the way we're used to working these problems. But we have to deal with this first. We have to view this as a unit and do what's necessary here before we can bring in the or statement. So throughout, I'll often put these parentheses in. I'll usually remark that I'm putting them in. You'll probably get tired of hearing me say that the parentheses aren't necessary, but I'm putting them in because it makes things more obvious. But anyway, so disjunct takes precedent over conjunct. Those are the basic precedent rules for Boolean algebra. There are some others with the nands and the nors. I'm not going to get into them just yet. They're not necessary for any of this. So, okay. That takes us then to problems. Let's go ahead and start working. Just think if there's something else I needed to do. Nope. That takes us then to problems. Let's go ahead and start working some of these problems. Our first problem then is actually demonstrates very well what we were just talking about with this idea of precedent. Our first problem, A, gives you the expression A or A and B. Now, there's a strong disposition, I think, to try to put these A's together as A or A and collapse them based on the idempotent rule. But we can't do that because the conjunct takes precedent. So we have to deal with this first, which means we can't just pull this little piece of that unit out. So really, this is again why I like to put parentheses in things into things. It kind of keeps me honest. You know what I mean? It's somewhat paradoxical, but it's really easy to lie in logic. And by that I mean it's easy to make very simple mistakes. It's easy to treat the or as an and. It's easy to forget that the conjunct has precedent, and so to do something over here first, etc. So these little mistakes are really, really, really easy to make. So I find that keeping myself organized and putting parentheses even if they don't belong tends to make things a lot better. It prevents me from making these silly little mistakes. Okay. So now there's another strong disposition, at least with me. I'm a big fan of the distribution rule, and I always want to distribute these. The problem here is it tends to just simply swap the signs. So I'll demonstrate really quickly. And you can do this. You can have 8 steps of distributing and redistributing and redistributing and putting things back the way they were and then back the way they weren't and then back the way they were again. It does, as long as you're applying the rules, the laws properly, it makes no difference. But if you do distribute this, what you get is A or A. So you get an A or A and. So our minor sign becomes our major sign becomes our minor sign. A or B. The A's then collapse, and you're left with A and A or B, which is, you'll note, is exactly all we've done is swap the signs. If I distribute one more time, all I'll do is swap the signs again. This can be very, very, very frustrating. So rather than doing that, I would rather note that this is an instance of the absorption rule because I have A or A and some Y. It has the form of A or A and some Y, which of course is going to equal A, because then it's just a one-step proof. I can just come down here and say, this is A. Oops, these need to be numbered. Sorry about that. From line 1 by absorption. I do require you to write down the line number and what rule you used. That's very common in logic. So it's just the convention. It slips a lot in the Boolean world. I think people just tend to treat it like math. They just do it. You'll see about 50% of the people actually write down the rules they use, and about 50 don't. But for this class, I would like you to write down the rules. Okay, so that's the solution to A. It doesn't get any simpler than A. We can't simplify that anymore. It's an atomic unit. We can't chop it up. So moving on then takes us to B, which is similar, and we'll get, see, so B is A or not A and B. Again, note no parentheses are given in the expression given to you in the problem, but we do need to recognize that the conjunct takes precedent. So I'm going to go ahead and put the parentheses around that, even though they're not necessary. Keep myself honest. Unlike the last problem, A and not A are not the same sign. So this isn't a form of the absorption. I don't have, sorry, that should be or, not A. I don't have A or A and Y. I have A or not A. So it isn't, it is not this rule. I can't apply this rule because this sign and this sign are different. In this case, distributing is going to make things a lot better. In fact, it's the only thing we really can do. What's nice about it is anytime you see these opposites, if you can distribute them, you'll note that based on the comp rule, they will actually either, if it distributes to an and, which in this case it will not, it'll distribute to an or, we'll get A or not A, and that'll collapse into a 1. If it were the reverse, we'd get A and not A, which would collapse into a 0. So anytime you have complements like this, keep a thought about distributing them and having them collapse. It's not always the right move, but sometimes or often. So I'm forgetting my line numbers again. Okay. So on line number 2, I'm going to go ahead and distribute this. So our major sign is going to become our minor sign. Our minor sign is going to become our major sign, and we can sort of remember that, or at least I find it easy to remember it as A or not A or not A. So it's this or the first thing, and this or the second thing. And I say this or because it brings to light this idea of forms, that we're using forms here. A or B. So we don't get wrapped up in it having to be a singular constant that we're dealing with. This could be an expression, a sub-expression all of its own. So, all right. That's from line 1 by distribution. And then we see that the A or not A is the same thing as our complement rule here, the disjunct side of our complement rule. So that's going to collapse into 1. So we can do that here as 1 and A and B, or B, sorry. See, it's very easy to get these little signs mixed up. A or B. And that's from line 2 by our comp rule. Now, you might be somewhat tempted to try to distribute this in, and technically speaking, you can distribute a literal in there. It's just not usually necessary because the literals tend to drop out, and by that I will show you. Note that if I commute these, that is, if I swap their places, commutate. The difference, commute is to drive to work. If I commutate these, I get A or B and 1 from line 3 by commutation. And we'll note then that this really has the same form as this identity rule here, whereas we see this as this unit right here as A and 1. So what that is going to equal is A, and that A is actually the whole unit A or B. So we can go ahead and do that. So we can say that this on line 5 is equal to whatever A stands for, which in this case is the unit A or B. And don't need the parentheses here because there's nothing else. There's nothing to hold out. Okay. So this is from line 4 by our ident rule. And this is as small as this is going to get. So we're done with this problem. Now, some things, I should say, some things you can do on one line. That is, I didn't really need to commutate this on its own line. I will, generally speaking. You don't have to. The things that you can do, you don't do everything on one line. That just makes your logic illegible. Like no one can follow it. It becomes very obfuscated. But certain things become very redundant. And those things that are like, oh, yes, we know A and A is A. We don't need to see it. Or those can be flipped around. It's quite obvious. So generally speaking, people allow those to be doubled up on a line. So the ones that we can double up on are our comp rule can be doubled up on. Our indefinite rule, of course, the collapsing letters can be doubled up on. Decomp, the double complement, can be doubled up on. So this one, this one, this one, commutation and association can be doubled up on. So what, about 50% of them you can double up on, the easy ones. And when you double up on it, what I mean is that you write it down on one line. So if I started back at line 3, right, and I was sitting here at line 3, and I had 1 and A or B, what I can do is simply, that was from line 2 by comp. What I can do is I don't need to flip these first. Everyone can see that it is simply the reverse of this identity rule. That if I do flip it, I get this identity, I get the form of this identity rule. So we can say on line 4, we can simply say A or B from line 3, and we have to record everything we did in order. So we first commutated it to put it in the right form, and then we applied the ident rule to drop out the 1. Okay, and I said drop out the 1. People tend to treat it that way. If you watch videos on the internet, they just say, "Oh, the 1 goes away," which, yeah, okay, more or less it does. But really, it's just results in the 1 A and 1 is A. So I guess it just depends how you look at it as to whether the A or the 1 just drops out or not. So anyway, okay. Next, C. A and not A or B. A and not A or B. The parens, or parentheses for parens is a short slang for parentheses. The parentheses are given in the equation or the expression because they're necessary here. Without these parentheses, we would have A and not A as our primary thing. We would have, if we didn't have the parentheses, if they were listed like this, if it was listed, the expression was listed this way, this can go first, so I could simply collapse these into 0 or B, and 0 or B is, of course, B, and so it would collapse like that. However, the parentheses are given, so we know that we must deal with this first because we have to deal with what's in our parentheses first. Okay, so let's go ahead and do that. I do note that I have an A and not A. That's really happy. If I distribute these out, I don't have the absorption form because my front two terms are not the same. A and not A is not this, they're not the same term, so I can't use my absorption rules. So I can't use those. But I do have opposite terms. So when I distribute it, I will end up in this identity moment. So let's go ahead and do that. So sorry, not that identity moment. We will end up in this identity moment. We will end up in this identity moment here. So we distribute them. Our major sign becomes our minor sign. So we have A and not A. A and not A. Or A and B. Or A and B. Okay. This is line 1. Line 2, we derive from line 1 via distribution. And then these, of course, collapse on each other based on, why did I do that? That was really weird. Sorry, the idempotent rule, not the, the comp rule. Wow, I am just doing batting 1,000 here. So we're at the comp rule here. A and not A is equal to 0. 0 or A and B. So we see it's very similar to the last one we did. This is from line 2 by the comp rule. We can see it's very similar to the last one we did. Here, last time we had a 1, this time we have a 0. Makes no difference. Our ident rule, of course, we can see that this is, if we commutate this, we're going to get this form of A or 0. And by that, we see that if this is 0 or, and this whole thing is A, then if we flipped that, we would get A or 0, which, given this rule here, is going to equal A. So that's what I'm looking at as far as my forms go. Okay. If you don't want to flip this, if you want to kind of just jump right into the ident rule, that's fine. I'm going to go ahead and commutate it just in case some of you aren't still really comfortable with that. So I can flip these. I really shouldn't use that. I think in British, I think that means very something different in England. I think I don't think it means, well, kind of flip at any rate. A and B or 0 from line 3 by a commutation. This, of course, as I just said, is our ident rule for our disjunct side as A or 0. So we're going to go ahead and do that, then that just results in A, which is this first whole unit here. So we have A and B from 4 via our ident rule. And that's as far down as simplified as this expression is going to get. Okay. Next, D says X or Y and X or Z. X or Y and X or Z. That's line 1, 2. So we have like terms here. So we could distribute this out basically our major sign becomes our minor sign becomes our major sign, and we pull the x's out. So we have x moving our minor sign to our major position, and then our once major sign, now our minor sign, links the two last terms together, y and z. So we have y and z. Okay. And that's from line 1 via distribution. And that's as far down as simplified as we can really get this. There's nothing else that's going to cancel out. There are no other like terms to combine or anything like that. And if you look at it in terms of ones and zeros, if you were to put this on a truth table, you would see that, if x is 0, the whole thing is going to be false. But if x is 1 and y is 1, but I'm sorry, the whole thing may not be. I'm treating that as an and sign. If x is 1, the whole thing would be true. If x is 0, but y is 0, then that becomes 0, or 0 becomes false. However, if y were 1 and z were 1, then that would be true. So it really is contingent. There's nothing more we can boil this down to or pull out of this to make it more simplified. Okay. Moving on then. E. E states that, let's see, x and y or x and not y. So x and y or x and not y. Note that the expression given to you in the problem does not have parentheses, simply because it's not necessary here. The conjuncts take precedent, and so they define a unit. As usual, I'm going to try to keep myself honest and put these in parentheses. I do have two y's here, the complement, y and y complement, so I know that those are going to reduce down probably by an or, and so they're going to reduce down to a or not a, which is a 1. I do have an x in my front term on both these, so I can distribute that out, which is going to throw my y's together anyways. So that's really tight. That's line 1. Line 2, then distribute this x out. X or, because our major sign becomes our minor sign. I'm sorry, that's wrong. Our minor sign becomes our major sign. X and y or not y. And again, I know I'm harping on this a lot, but our minor became our major became our minor to link together the last two terms. Okay, so that's from line 1 by distribution. Note that y or not y is equal to 1 via the disjunct form of our comp term, our comp rule. So on line 3, I can say x and 1 from line 2 by complement or comp. And then we note that x and 1 is our identity, the conjunct form of our identity. So we have this rule here. So on line 4, a and 1 is equal to a. So in this case, x and 1 is equal to x. And that's from line 3 via our ident. And we are done with this problem. Okay. That brings us to F. So let's do F. And F states A and B or not A and B. So it's similar to the last one we did. So we have A and B or not A and B. There's a disposition to try to distribute these because it's somewhat, and I'm not saying it can't be done. I'm saying that the drive to do it produces something that's a little bit wrong. You are seeing something when you want to distribute out the A or not A, but it doesn't really work that way. It doesn't match the form properly. And so we try to keep the forms intact as much as possible, with the exception of those like half that I said were very, very simple in nature. By keeping things ordered and organized and following the forms exactly, we prevent we ease up on our accidents. So there is a disposition to try to do something like A or not A to pull that out and go and make that an and, but that's not exactly right. So it's just easier to bear in mind that these are not like terms, so we can't pull them out as a unit using our distribution. Sorry, I was still wrapped up in the idea that you can distribute out multiple terms, but what happens is you need another term to go with this at any rate. Let's get into it. What I can do, though, is I do have B's which are alike, and so I can actually commutate my left hand unit and my right hand operand. I can commutate both of those, and that will actually allow me to pull out a like term. Again, commutation is something you don't have to record, or you don't have to put on its own line. You do have to record it. I'm going to go ahead and do it, but I'm going to do it 2 times. So I'm going to say I have B and A, or B and not A. That's from line 1 by a commutation 2 times. Okay. Sorry. Here. Now, having the B's out front here, I do have like terms in the proper position, in this proper position for pulling them out. So they are in the right position for this distribution. So I can pull out the B's. as B, our minor term becomes our major term, and the erstwhile major term now becomes our minor term, linking our last two together. So we have B and A, or not A. Okay. That's from line 2 by distribution. Again, if you'd put this on one line, if you'd done it all on one line, you would have put line 1 commutation 2 times comma distribution. So letting us know that you did 2 things, well, technically 3 things, but you kept record of everything that was done. Okay. Of course, the A or not A is going to collapse into a 1. So I have B and 1 from line 3 via a comp. And then B and 1 is the ident rule here. So that's going to equal just B. From line 4 via ident. And that one is done. Okay. So to G, then, not A or not B and not A or B. A complement, or B complement and A complement or B. Okay. Here, of course, again, basically the same moment. After we commutated the last one, the set in the last problem, we have basically the same thing now, except without the commutation because it's already set up in that way for us. That we have not A and not A are like, don't do that. Not A and not A are like terms, so we can pull them out, leaving B and, or not B and B behind. So we have not A, our minor term becomes our major term, or, and then our erstwhile major term becomes the minor term, linking together the last two constants. So we have not B and B from line 2 via a distribution. Not B and B, of course, is the conjunct moment of our complement rule. So on line 3, we have not A or 0. So that's what that gives us. Not A or 0 from line 2. Oh my God. From line 2 via complement. Sorry, this is a common error. I just realized that I recorded line 2 by distribution when really it was line 1 and I was dealing with line 2. So that happens. Okay, so that's line 1 by distribution, line 2 by comp, and A or 0 is our ident rule here. And I know it says not A, but that's okay because it's this term or 0. This something or 0 is going to be equal to this something. So it doesn't matter if that's an A or not A or not A or not B, whatever fills this space, this operand space right here, or 0 equals whatever's in that operand space. So we can, and in this case, it's a not A. So that's what that equals. So line 4, not A, from line 3 via our ident rule. Okay, and that is G. Moving on. Oops. H. H. Y or Y and not Y. Y or Y and not Y. Okay, oops, no parens were given, no parentheses were given. I'm going to put them in, keep myself honest. That's line 1. Line 2. There's a disposition to distribute this, okay? If you did, it's not a mistake. It may not lead anywhere because all you end up doing is swapping the signs, but it is not a mistake. By that I mean, oops, we can see that if we were to, you might have decided to go Y or Y and Y or not Y, Y or Y and Y or not Y, and that's fine. And it actually gets you somewhere in this case, because the Y's collapse on each other by the idempotent rule, and the Y or not Y become a 1. Y or 1, Y and 1, of course, via the ident rule becomes Y. So this could have been, this is a perfectly fine way to work this. It's great. Another way you could have worked this is to note that I have 2 like terms and in front, and I have 2 different operators. Sorry. So really, I have the A or A and Y. I have my absorption moment here, so I can just say that is, of course, going to be equal to whatever A is. In this case, A is Y. So this is just Y from line 1 by absorption. Either way is fine. It makes no difference. It's not even that inefficient. This is 1 line. This is 2 lines. Whatever. It's great. Okay. That's H. Moving on. I. X or not Y and X or Y. Right? X or not Y and X or Y. Yep. Okay. So again, our like terms can come out via distribution. And that would leave our Y and not Y and Y together on the back side, which is kind of nice because then we know that those will collapse via our ident rule. So on line 2, I can pull out my x's. X minor sign becomes our major sign, and then our the last major sign is now the minor sign linking together our end terms, not y and y, from line 1 via distribution. Okay. Not y and y is basically this after we commutate it. It's our complement rule after we commutate it, so it's going to result in 0. We do technically have to commutate it first, or at least write down that it was commutated. It isn't exactly in this form, and I know that seems really, really trivial right now. It's like, oh my gosh, it's just but it is a commutation moment that goes on there, and we do need to say that we did that. So on line 3, we get x, and I'm going to do it all on one line, or 0. But I'm going to note that from line 2, I derived this from line 2 first by commutating so that I could get these into the A or not A form, and then by applying the comp rule. Okay, so that gives me x or 0. X or 0, of course, from our ident rule, our identity rule, is going to be equal to x. So we put that there. So that's line 3 from ident. Okay. That takes care of I. On to J. A and B, or A and B or C. So we have A and B, or A and B or C. Oops, sorry, hang on a second. There are no parentheses there. Or A and B or C, and or B and B or C. Okay. And now, first off, of course, there are I want to put parentheses around here simply to keep myself honest as usual. And I'm going to work this in 2 different ways. I want to work this in a long way simply because I think that there's some interesting distribution moments in here. That said, there's a much shorter way of doing it based on the absorption rule. But let's start with our first way of doing it, and we'll work this first way in green so that you know that I'm going to go ahead and change up on you later. This has the form, and it's somewhat hard to see, which is why I want to do this. This has the form of, let me actually, in order to make that form more visible, let's do this. Again, I have an and sign here, a conjunct, which means that this takes precedent over this disjunct. So I'm going to go ahead and put this in a in its own little unit like this. These parentheses are redundant, but they do help shine a light on the fact that what I really have here is this A. sorry, hang on a second. We have A and B, or A and this whole thing takes the place of C, right? So that's why I wanted to work this way. Work this way first, because it really brings out. It's sometimes hard to see this distribution, which is fine in this case because there's actually an easier way to do this problem, but it is there. I do have like terms here or here, and I have some other term here and here is B and C. So I can distribute this. So let's go ahead and do that. Pulling the A's out. So this is line 1. This is line 2. Pulling the A out. So I have A. So I get the A from here and here. Our minor term becomes our major term. So that's an and. I then have B or C. So our major term, our once major term, now links our backsides together, or the ladder constants. So we can say B or, and whatever this C is, which in this case is B or C. Okay. Oops. And so that look like that, and then we just fill in, the whole rest of this term here, or this expression. So B and B or C, and that's from line 1 by distribution. Okay, so that's something it's sometimes hard to see that, and so I think it was really sort of worthwhile to go ahead and do this way, so we can see these more complex, these more complicated or complex distribution statements. 1, 2, 3, 4, 5, 6, 7. Oops. Okay. So now the next thing I want to note about this is that is interesting because we did this way, is that my parentheses here are somewhat unnecessary. This parenthesis is certainly necessary. This parenthesis here is necessary because it's separating off this and this conjunct here. But the internal ones, this B and C, are arbitrary based on the, well, not really arbitrary, but kind of based on the association rule. So, because each of these is an or statement, I can group them together however I want to, or just get rid of the parentheses entirely. It makes no difference. So let's go ahead and do that, so we can get rid of these. So I'm just going to get rid of these parentheses entirely. Technically speaking, via the association rule, I should be really putting them around the B's and dropping it off. The reason I'm not doing that is because, sorry, I've lost my cursor again. Hold on a second. The reason I'm not doing that, or the reason I'm going to go ahead and do that, is because, unlike propositional logic, Boolean logic does not have a requisite for binary grouping. Propositional logic, everything has to be in binary grouping, so I could not just get rid of those parentheses. I would have to move them. In Boolean logic, that requisite isn't there, so I'm just going to go ahead and allow the parentheses to be dropped as kind of a offshoot of the association rule. All right, anyway. B or C, of course, the B or B, these two will collapse on each other via the idempotent rule. I'm still kind of mispronouncing that. So I have on line 3 A and B or C or B and B or C from line 2 via my idemp rule. Okay. Now we see that we do have, these are units because of our conjunct. We really have a unit here. Hold on a second. And here. And another unit here and here based on the precedence of the conjunct. I do see that I have B and C as the same in these. So putting them in these parentheses actually makes things a little bit nice. So if I swap these, if I commutate these two operands, the groups in these two operands, I can actually distribute one more time. So on line 4, I'm going to go ahead and take B or C, swap that with its A, and A, and then go ahead and commutate this group as well. B or C and B, okay? And that's from line 3 via a commutation 2 times. You must put down the 2 times. Okay. Having commutated these, I now have my 2 like terms out in front, so they're in the right form for distribution. So I can pull them out, making my major operator, or my minor operator, my major, my major, my minor. So we have B or C, take the minor, make it the major, and A or B. That's from line 4 via distribution. Line 6, I note again that I have common B's here, different signs, so I once again have a distribution moment. Again, make sure you check those signs. It's important. It's easy to miss. I would need to technically commutate this first. I'm going to do it all on one line. So I'm going to pull the B out. And then, so that's B. My minor sign becomes my major. Or C, and if I commutated, the A would be on the backside, so C and A. That then is from line 5. First off, via commutation, and then via distribution. This is probably its simplest term. I don't need the parenthesis. You can get rid of them if you want, simply because the and takes precedent. You could get rid of this, but you don't have to. You could get rid of that. I'm not going to. I'm just going to leave it. I could distribute this out. It really wouldn't make the term more simple, so that's kind of going the opposite way. Well, and in fact, it would put us back here anyways, so yeah. Okay, so that's done that way. Let's go ahead then and look at the other way to do this. Let's see. So we'll get this all down here. Sorry about this. 1 second. Okay. Oh. Let's just leave that. Oop. Here. Okay. Put this back in our blue. Okay. So this is line 1. We do note, you can note that this is 2 like terms separated by an and an or. So really, what I have is, what I have here is A and A or Y. Okay, so I do have my absorption moment here that I can apply. I also have it, yeah, I have it there. And that is about it. I had that somewhere else. Okay, so I can apply that right away. So on line 2, you have A and B, or A and B or C, or, and this just collapses into B. Now we can see that I really have some term A or some term B or some term C. So I can commutate these and move this B over here and distribute it into this, or I could do what I did last time and distribute this into this. I'm going to go the opposite way just to change it up a bit. So I'm going to commutate these. So I'm going to move my B over here. And technically I'm commutating twice, and it's somewhat hard to see. I have to commutate this one and this one. And then I would have to commutate this one and this one. So I'm technically commutating 2 times in order to get, oops, B or A and B or A and B or C. Okay. Oops. Let's record some rules. Oh my word. So this was from absorption from line 1. And this is from line 2, commutation 2 times. Okay. Having this here, I can now distribute this in. So on line 4, I get B or A, my major sign becoming our minor sign then becoming major, and B or B. If you'd like to just recognize that those are going to collapse on each other and put it and just collapse them into one and put it down that you did that, that's fine. I'll wait to the next line. Let's see, so because I haven't done this rule a lot, and then this leaves A and B or C. So here, that's from line 3. Again, don't forget to record if you collapse those in one fell swoop. Don't forget to record that here, but that's via distribution. And then if you did the collapse, you'd put the rest of that out there. Okay. 5. I'm going to go ahead and apply the idempotent rule now. So we have B or A and B or, and mind you that again, this dictates kind of a parenthesis here, although it's not necessary. It does just to keep the precedent in order. So that's we collapse by idempotent, and then we have A or B and C for by idemp. Okay. Finger. Woo. Don't do that. Don't do that. Don't do that. Cancel. Please cancel. My gosh, that was really close. I'm gonna delete everything right in the middle of my video. Oh my goodness. Okay. 6. Okay, so distribute this out in here, commutate it, then distribute it. I'm going to do that all in one line. So I have, and again, B and B will collapse. Or, sorry, let me just go ahead and do that. I have B and B, that will collapse. Or B and A. So I'm going to go ahead and collapse that B right now. So I'm just going to collapse that B right now. So we have a B here. Or A and B or C. So I've commutated line 5. The first thing I did was swap the positions between these two. So I commutated. I then distributed. And then I applied the idempotent rule in order to collapse those. So I had 3 things that I did on that. And you do need to record all 3. And then this goes here. So, okay. Now, if I distribute this, I will get another OR, which will be kind of happy. And note that it'll also give me a B and an A together because the major sign will become a minor sign. So that'll give me my B and A together, which will match this. It will also make this OR a major sign, which means I have something or something or something or something, in which case that will allow a lot of recombination and such. So I can do that. Did I say at the beginning of this was a faster route? Okay. So I have B or B and A, or, and then distribute these. A and B, or A and, A and C from line 6 via distribution. Okay. Note that these parentheses are no longer necessary because we have or, and so they're not blocking anything off. They're just separating out. This has the form of P or Q or R. So they're not really necessary in this context, so I can drop them. Come here. Take that. Okay. So let me get my eraser here and get rid of them. Okay. All right. This then allows me to see this then allows that, come here, this then allows us to see that we have a B and an A and an A and a B. So if I commutate those, they will collapse together. So on line 8, I get a B or B and A, or A and C. This is from line 7 via commutation and an idempotent rule. And it's important that you see that. It's important that you see that this is that once swapped, B and A are identical. So it is A or A. So it's important that you see that it's some identical thing, something, and something else is identical to it. So that's the idempotent rule. Okay. Line 9 then. We have two choices. We can pull the A out of this, or we can distribute the B in. Thus, these two B's will collapse, leaving us B or A. So let's go ahead and do, let's see, 1 second. Go ahead and do the this last one. I'm not sure that it makes much of a difference, really. So I'm going to do that. So I'm going to commutate this term here and then distribute out the A's. So I have B or, and then the commutation is A, our minor sign becomes our major. This again puts parentheses back in things. A and B or C. Yeah, that was probably the wrong way to go. 8 by commutation and distribution. And then I'm going to, pardon me, it's going to get really slightly weird here for a second, so I'm going to move this up. So we're going to kind of lose our rules for a second. I apologize for that, but that's all right. Okay. Now on line 10, this creates a situation where I have to distribute this back through and then distribute the B back in again to sort of whittle it down. So we're going to take B or A and B or this term. So it's B or A and B or B or C. That's from line 9 via distribution. Note then that we have or signs, so this inner parentheses here are not necessary, or I could simply, I can get rid of them or I can reassociate them. hang on, there we go, okay. Or I can reassociate them. There we go, okay. So I'm just going to go ahead and, dang it. Stop that. I don't know why it's getting hung up on that. Stop. Just a second. Okay, so we can get rid of the parentheses like this. And then, all right, that. This program decides that it wants to do its own thing from time to time, and so I had to go whip it back into submission. Okay. The B here and this B here will collapse together based on the independent rule. So on line 11, I get B or A and B or C. From line 10 by the idempotent rule. I now have B out in front, so I can pull those out. Good grief, this was long. So I get B, minor sign becomes a major sign, or the once erstwhile major sign, now our minor sign, links together our last two elements or constants. So we have A and B. A and C. So this is distribution from 11. And this is as simple as our expression will get. That was a lot. It really wasn't. I've seen proofs go like 50, 60 lines. They're more in the propositional logic moment. For a Boolean expression, this was pretty intense, but for logic in general, moderate. Okay. So let's go and put things back the way they're supposed to be. And that's here. Let's get this there. And then go ahead and delete that. So that was J. So we're now on to K. And let's see. So K. And K is W or not X or Y or not Z and Y. Here. W or not X or Y or not Z and Y. Okay, so this one's got a couple of interesting moments to it. Initially, not just initially, but there's a drive to, you can distribute this in here and put the Y's together, and then it will, they will collapse. And we can do that, and let's go ahead and then. But there's also another, as with the last one, there's another thing that we're kind of can do to this. So let's go ahead and do that first one. We'll work this one two ways as well. So technically, I should distribute these first. So I'll go ahead and do that. You don't have to. You can put it all in one line. Y and W or not X or Y or not Z from line 1 by a distribution. Sorry, by a commutation from line 1 via commutation. Now I can distribute. So I get this Y and W or y and not x. I know the parentheses, of course, are not necessary, but they do make things happy. Y and not y. I'm just going to go ahead and collapse that right now. Or y and not z. So from that's line 2 via a distribution. And also I decided to do an idempotent in there. So we had that as well. Okay. So here now what we have is, and it's somewhat hard to see, I guess, but we have y's all the way up and down. We could pull them back out, and you would get this y or w and y and w or not x or z, not z. But you can also see that we have a y or y and some other thing, which is the same as our absorption rule here. So I could apply that at this point. So let's go ahead and do that. So we could have on line 4, we could have y or y and w, or y and not x, or and here we're going to take y, and y or not z is simply y. So we have that from line 3 via our absorption. Sorry. I'm just laughing because there's this like cascade failure. I can sort of see how Data's positronic brain might have, suffered a cascade failure. Yeah, I watched way too much Star Trek as a child. Oh wait, no, that wasn't Data either. It was Lal. Yeah, it was his daughter that suffered. Nobody really cares. So sorry. Moving on. Yeah. Okay. Point being, though, we do have another moment of this here. It's going to simply fail again, and then it will fail, not fail, but it will collapse again, this cascading collapse. Because if we swap these two terms here, we get y and, say y or y and not x, which is, again, this same term here, or the same absorption rule. So on line 5, I'm going to go ahead and commutate and apply the absorption rule all in one. So yes, I'm still giggling about that. It's a sickness. I'm seeking help. Okay. Plus y, so I swap these two and then apply the absorption rule. So from line 4, I have first off a commutation and then an absorption. And okay, and then we'll do that one more time. Again, if I swap these two, I note that I get a y or y and something else. So that results in a y based on this absorption rule. So from line 5, let me back up just in case people aren't seeing this. I'm kind of worried that they're not. I'm gonna swap them first. So I really have y or y and w. So that's from line 5 by a commutation. And then we can see that that really very much is the A or A and Y rule that I have right over here. And that, of course, is going to equal whatever stands in the A positions, and that in this case is the constant Y. So on line 7, then I can simply say Y because that's what sits in this position, based on line 6 via absorption. Okay. That's fairly easy to see when you think about it, because excuse me for a second. If Y is a 1 here, then it's a 1 here, and since these are all OR statements across here, that's enough to make that all true, so I get a true and a true. If Y is a 0 here, then it doesn't matter. So really, none of these other things make any difference, because the Y commands over both an disjunct and a conjunct, which is really the same thing that the absorption rule applies. So we can see that, oops, we can actually, knowing that, we can actually see this if we commutate these a bit. We can see that it could have been applied right off the bat. So let me get rid of some of these. Excuse me, I got something in my throat. It's just, ugh. Okay, so let's get rid of this. Okay. Okay. Okay, so bring this back to the blue. We'll do it this way. Excuse me, sorry. If I commutate these, I get Y and W or X or Y or Z, not Z, sorry, from line 1 via commutation. Then if I commutate these once and then again twice, I come up with Y and Y or W or not X or not Z from line 2 by a commutation 2 times. Okay. Now it's fairly easy to see, or maybe not fairly easy, but we can see that this is A and A or all of this as some Y. So it is again our absorption rule, A or, oops, sorry, not that one. It is this absorption rule, A and A or Y. A and A or Y. So this is going to equal whatever A is. So on line 4, we can just say that this is Y based on line 3 via absorption. Okay. Okay, so that's basically it for K. Moving on then. So that brings us to L. Excuse me. L, which is W or W or W and X. W or W or W and X. Excuse me. Now, there's a disposition here to distribute things. Given all the W's, it just looks like distributing this through would be somewhat useful. The first thing we have to pay attention to, though, is that we have opposite signs here. So we can't distribute this W in that way. We can distribute this one, and it looks like it might be somewhat useful to do that, because what that ends up doing is swapping these signs and allowing us to distribute this WN. Ultimately, you end up sort of spinning your wheels with it, and we'll walk through that really quick. So if you take W plus, and then if we distribute this W or W and W or X, W or W and W or X, this collapses based on the indefinite rule. W or W and W or X. I've now successfully created a situation where I do have opposite signs, and it looks like I can distribute that in. You can distribute it in. That gives you W or W and W or X. And it's very useful, I find, to go ahead and make these notes on the side of your sheet. If you get stuck, just work the rules. Just keep working until something pops up, and it usually will. So that's why I'm kind of doing it in red over here off to the side. First off, because it's just one way to do it, and I'm just sort of basically kind of taking notes and dragging you with me. Congratulations. Let's see. The W's collapse via the indefinite rule. So I'm left with this, and what it starts to look like really what's happening is I'm really just swapping signs at this point. I haven't successfully gotten rid of any of the W's. You'll note that I guess I did get rid of one. I started out, no, I didn't. I started out with 3. I still have 3. All I've done is basically, I've managed to get these into opposite signs, which is nice. Oh, okay, I can do this. So, and this is what I mean by stuff popping up. I hadn't seen this before. These are all or signs, right? I have an or, so I can go ahead and lose these parentheses. I don't need them because since it's all or signs, it makes no difference. These parentheses are superfluous. That now allows me to group together these two W's, and they will collapse. So I now have W and W or X. Okay, yeah, this is going to work. Distributing this one more time, I get W and W. Or W and X. The W's then collapse by the indefinite rule. So W or W and X. Now I have to do something else because I'm just going to, if I keep distributing, I'm just going to start swapping the signs every time. But I can see it does make it maybe somewhat easier to see at this point that I really have A or A and something, which is going to equal whatever A is. In this case, that's W. So here I can just bring this down to W, and I'm done. Which makes sense. I mean, again, we have the situation where W is commanding over, or taking part in, I shouldn't say commanding over, but taking part in both a disjunct or a conjunct and disjuncts. So we're always going to get this kind of moment. So that would be one way to work it. Another way to work this is to realize that here I have that same moment. In fact, this here and this phrase or expression here are exactly identical. So if I could see that earlier on, then I could simply realize that this is A or A and whatever, and then I can work it like this. To W or W and X is going to be equal to W. I don't need parentheses around this anymore. So that's from line 1 via the absorption. And then W or W, of course, collapse in on each other via the idempotent rule. Sorry, it's this one over here. It's a disjunct form of it. So we have W from line 2 via the idemp. Okay. And that basically, more or less, two different ways of working this problem. You sort of end up here anyways. You can see where the absorption rule is really useful for getting you out of that very irritating distribute back to what you had, distribute back to what you didn't have, and distribute back to what you had again. If you get caught in a loop like that, look for your absorption. It might be there. Probably is. Okay. That takes care of L. M. Let's see. M is very similar. So we have M. And I should have probably just let you work M on your own. It is just that similar. We have X and X or X and Y. So some things that are different, you note that our signs here are different. They were the same before. So all the way through we have opposite signs. So it looks like it might initially be a bit more, a bit more forgiving for distributing, but we don't really need to. Again, if we kind of remember this fact that we really have A or A and something else, which is our absorption, the disjunct form of our absorption rule, then we can see that that simply is going to collapse as an X. So that makes solving this really very easy. So this is line 2 is X, and this whole thing collapses into X via line 1 absorption. X and X, of course, gives us X based on the idempotent rule. Still not sure I'm quite pronouncing that right. I know I'm close. I'm really close. So that gives us X from line 2 based on the idemp. And we're basically done. Okay, so that takes care of, well, let's see. If we wanted to, we could do this a bit to, again, to some degree using distribution. So, and I think it's somewhat useful to do that. I think it just, people forget to swap the signs. They forget to, especially when you're dealing with complicated terms, it gets somewhat confusing about, how that really plays out. So we'll look at this real quick. We'll just, plus X and Y. Our signs are opposite, so I can distribute the outer term in. I could distribute these as well, but it's going to be a little bit more useful, I think, to distribute the outer term in. Note that this is A and B, or this whole thing here as C, and that can get somewhat confusing. So if it's easier for you, I find that sometimes going ahead and doing that sort of math replacement moment where I'm just going to make this equal to C, and then I'm going to distribute based on that and then swap it back out for what it originally was. So we'll do it that way. So here I have X and X. Remember my minor term becoming my major term, or my major term here becoming my minor term, X and X. And this doesn't quite look like a minor term. This one looks like the minor term, but remember we're counting this as C, and that's one of the nice ways to do that, because then I can see that that is, come on. I can see that that really is X or C. So I can see now it's much clearer, much easier to see, much more clear that this is our minor term. So that's that becomes our major term, or X and C, and in this case C is X and Y, so I'm going to go ahead and swap that back in. So I have X and Y like that. So that's from line 1 via distribution. So again, that's a pretty useful trick to just, pull this term out and replace it with a singular thing, and then put that term back in, that whole complex term back in after you've done the distribution. Okay, couple things happen. This, of course, these collapse. So I have X or X and Y. So that's from line 2 by idempotent. Note that I have conjuncts all the way through here. All the way through here I have conjuncts. So I can redistribute these, reassociate these together, and then the X's will collapse. So on line 4, I get X or via an association, because I'm going to reassociate these here and here via an association and a idempotent. I get x and y. That's from line 3 via a association and an idempotent. At this point, I think if I start distributing through, I'm going to start this cycle of just swapping the signs, which is somewhat frustrating. Easier or better to see that, again, what I have here is A or A and whatever, which is going to equal A. So seeing that, I can apply my absorption rule very quickly and just finish this off as x from line 4 via absorption. This was just nice to see some of this distributing here, this more complicated distributing. I think it's important to see that and work with that a bit until you get comfortable with it. Okay, so that's M. Let's move on. M, and then so we're to N. And N is our first introduction. Oops, let's not do that. Let's go back to the blue is easier to see. N is our first introduction into the De Morgan's realm of things. We haven't had any really De Morgan stuff yet, not much negation at all. So N has the expression A and B. And, oh, sorry, wait a second. There's no parentheses there. And, that's not right either. Sorry. Not A or B and C. And all of that is negated, or the complement of that, whatever that is, whatever comes up for that equation. All right. A couple things to note. The parentheses are important here. They make sure that we're doing the disjunct before we do our conjuncts. The conjunct would otherwise have precedent. We don't have parentheses here, and we could put them in, and it might make things somewhat useful to do so. Do this then. Okay. We can't distribute anything into this because it's all bound up with a negation. We actually have to deal with this negation before we try moving anything out of this or moving anything into this. We actually have to deal with this negation first. So our De Morgan's rule says that any statement of A or B, that whole thing negated, which is what we have here. We have A or, and this whole thing is B. I'm careful with that line in this case. This whole statement here as a B, and that A is negated. That whole thing is itself, actually, let me, that A, I don't want to negate that because it's, the form is not negated, so I don't want to negate that. The form is A or B, so I don't want to negate that. So I have A or B, and that whole thing is negated. We can see that A or B, and that whole thing is negated. That, of course, is going to equal then A negated, swap the sign. Oops, swap the sign. I just said swap the sign. B negated, okay? So we can just put that in there. That's line 1. So for our line 2, we get A and B, and this negated and that negated. So I have a double negation here because I've negated the negated. And B and C. And since this is all B, since this whole thing is this term here, this whole thing gets negated. And that could be somewhat trouble. If you were tempted to negate each of these, you would have ended up with a bad situation, because what you would have done is you would have ended up with yada yada, A, not, and not B and not C, which is different from what we're going to end up with, which is A double negation and not B or not C. So you would have been off on that sign, which would have caused a fallacy in your calculation. So we're going to make sure that we don't do that. And we have this here. And I'm going to go ahead and put our brackets back in here so we can see those are parentheses. Okay. I'm not going to write my rule here right now. That's, well, let me just put it up here. From line 1 via De Morgan's. Okay. The reason I'm not doing this, I want to leave this in here so you can see that this is really what we're going to end up with. I can I'm going to double negate this and do the De Morgan's rule again on one line. So I'm going to A and B, and via a double negation, I have A and B or not B or not C. So remember, we have to change the sign when we use the De Morgan's rule. So we have a not B or not C. And that is, I apologize for writing these rules all over the place, from line 2 via a decomp, double, see, and then a De Morgan's double complement and De Morgan's. 4. Now I have a couple of choices. I can try to distribute this through, or I can note that what I really have here is I can put parentheses around this. No, that sign would have to be different. I can move this over here. Nope. Okay. So what I have here is conjunct, 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 or in other words, X and Y and Z and P kind of thing. Oops, actually, I don't even need that. I have X and Y and X and Z. This whole thing becomes Z. So I have nothing but a string of conjuncts. I can move these parentheses around or just get rid of these outer parentheses. I can't get rid of the inner ones. They're very important that this remain a group unto itself. This makes it a group. I can deal with it as a whole unit, but I can't separate it out and let it intermingle with the rest of the crowd because it's an or and the ors don't get along with the ands. It's kind of this whole sinist thing. Anyway, okay. So let's go ahead then and regroup our stuff together using the association rule and the commutation rule all at once. So that gives me, using association and commutation, I have A and B and not B or not C. And that is from line 3 via combinations of association and commutation, one each. Association and commutation. So in other words, I reassociated these together and then commutated those. So to get this, I left the parentheses off. They're not necessary in this context. Again, if you were working with propositional logic, that would be different, but we're not. So A and A will collapse down by the idempotent rule to A and B and not B or not C from line 5, not, from line 4 via the idempotent. Okay. I can distribute this through here, thus combining my B and my not B, or in this case it will be B or not B. So let's go ahead and do that. A, and then we distribute this B or not B and B or, sorry, that's not right. I have my minor and my major mixed up. B and not B or B and not C. Now, B and not C. Note that because I distributed this through, because I pushed this into these parentheses, I've made a unit out of this, okay? So we have to honor that. So I'm going to put up those parentheses. Otherwise, I would be able to shuffle these around in ways that I really shouldn't be able to do. I have different signs here, so I have to make sure to sort of honor which is grouped together. Okay, so there's 7. And that is from line 5 by distribution. Okay, B and not B, of course, is our comp rule here. So I have A, and that gives me a 0. 0 or B and not C from line 6 via comp. Note that this is just the flip of our ident, the disjunct form of our ident rule here. So if I commutate this, the 0 drops out, if you care to look at it that way. Or we can say that it's equal to this as B or C. So I have A and B and not C, based on line 7. First off, by a commutation to put it in the proper order, that is the proper form, and then an identity. Okay. Now we can see I have am terms all the way across. I can't do anything much more with this. This is in as simple as terms as it's going to get. Okay. So that's in. And again, note the important thing here is that when this collapsed onto this A, this became a decomp moment, but it remained over this whole B or C here as a single unit, as A and this whole thing B. So when this collapsed, when I brought this down and changed the sign, I had to make sure that I kept it over this whole unit, and that's really important. Then when we broke it down again, we know that our signs went ahead and changed so that we ended up with this instead of that, which we didn't want. Okay. Alrighty, that's in. O. O gives us X or not X, and that whole thing, the complement of that whole thing. So I have X or not X, and then that whole expression negated. Okay. This is fairly straightforward, not nearly as hard as the last one. By the De Morgan's rule, any statement of that's A or B is equivalent. The complement of A or B as a group is equivalent to not A and not B. So I can just say that this is equivalent to not A and not B. From line 1 via De Morgan's. Note, I could have double negated this right away on the same line if I wanted to. I don't really have to go down another line and do that, but it doesn't matter. You can. A and, so not X is our decomp, so that's just going to end up in X. So that's not X and X via line 2, double complement. Note that here we have a contradiction. It's X and it's not X all at the same time. Can't be the case. But this is the form of our complement, the and, the conjunct side of our complement rule. So after I commutate it, I get this form here of A and not A. So on line, and that equals 0. So on line 4, my final answer here is 0, based on a from line 3, first off by commutating, and then applying the complement rule, complement law. Okay, and that is O. Okay, let's see. P, our final one. Not X or not X, all that complement. So not X or not X, and that whole expression itself negated. So that's line 1. Again, we can see kind of what's going to happen here. This is going to, is it an or? Yeah. This is going to collapse onto these two, changing the sign and making two negations here. So let's do that. So based on our, just bear with for a second, this has the form of A or B, all of that negated, where A is equivalent to not X and B is also equivalent to not X. But that gives us this moment of our De Morgans. So we can simply, once we negate our A, so if A is not X, we negate that, change our sign, because we have to change our sign here. And, not B. B is also equivalent to not X, so we negate that, negate our B, so we get not X and not X from line 1 via De Morgan's. Again, if you'd wanted to double negate decomp twice, you could have done that here. I'm just going to do it here. So I have X and X from line 2 decomp 2 times. Okay. X and X, as we've seen, is simply X via our idempotent. So this just boils down to whatever X is. Cool. Line 3 via our idempotent. Okay. I know this is long. I hope the practice helps. As with anything, or as with logic, this kind of manipulation of logic laws in order to work through problems, practice is everything. Do these again if necessary. If you want more, I can certainly I have more problems for people to work. Again, practice cannot be overstated with this. I think I mentioned earlier, if not, memorize the rules as best you can. If you memorize these rules, it will make seeing these patterns so much easier, because your brain isn't fighting with, wait, what rules? And you're not searching through trying to see, it's like, oh, wait, that looks like this. If you memorize these rules, you'll find that this goes a lot more easily and can actually be somewhat fun, because it really is just a logic puzzle, if you think about it, quite literally. Okay, I hope this helped, and thank you much.